Good afternoon. Thank you so much for coming. If you are here, you're attending the SANCOLD YPF webinar for the raising of Gcuwa Dam, as presented by Benjamin Oberholzer and Londeka Mguni. If you have any colleagues that should still come, please send them a reminder. But okay, I'm going to start. Please note that we are recording. If you have any objections, please let me know. Welcome to today's webinar. I'll be your host, Ashley Gcuwa, and I'll be guiding you through this session. I'm an active member of the SANCOLD Management Committee, and I currently hold a social media position in the Young Professionals Forum, and I also work for the Department of Water and Sanitation. I'd like to thank each of you for joining us and giving us your time. Your presence highlights your dedication to staying informed and engaged in the field of dam engineering and design. Especially those with experience, we really appreciate your engagement. It's an opportunity for us to learn as well. I would like to introduce our speakers for today. We are so thrilled to have them and thank them for bringing their time and their experience for us to learn and engage and to discuss the choices that they made during their involvement in the project of raising Gcuwa Dam, which is a very important subject, especially when it comes to dam safety and, extending the resilience of our country in terms of water supply. So first up, we have, it started at the wrong page. We have Benjamin Oberholzer. He has over 5 years of experience in dam engineering with experience in feasibility studies, detailed design of composite dam raising, spillway hydraulic and structural design, dam break analyses, hydraulic model studies, monitoring instrumentation, construction monitoring, dam safety evaluations, and project management. He has worked on rehabilitation and raising of various dams, including Clan William, Gcuwa, and Tata dams, as well as the design of new dams such as Kwabeni and Zalu dams. He also has a master's degree from the University of Pretoria and is currently working as a production engineer at the Department of Water and Sanitation, specializing in concrete dams and hydraulics. Londeka Mguni has 7 years of experience in dam design and analysis, covering various dam types, including earthfill, rockfill, and gravity dams. Her experience extends to dam type selection studies for new dams like Zalu and Kwabeni Dam, pre-feasibility studies for dam raising such as Klipfontein Dam, and preliminary and detailed designs of dam raising, Gcuwa and Clan William Dam, among other projects. She also specializes in dam safety evaluations, project management, tender and contract documentation, and cost estimation. She has a civil engineering degree from the University of Johannesburg and is also a production engineer at the Department of Water and Sanitation, specializing in embankment dams. So without further ado, I would like to give over this virtual stage to our presenters. Please engage and ask questions within the chat feature. At the end, we will try and address all of them. So if you have any kind of questions, please feel free to post them there. During the discussion, you will see that your mic and video is off. So unless I activate it, you won't be able to communicate. So please use the chat function, and then we can decide later if we want to activate your mic, depending on the size of your question. All right, Benjamin, you are welcome to share your screen.
Okay, here we go.
Thank you.
Please,
it is visible.
Can you hear me? Can you see me?
Yes.
Okay, sure. Let's go ahead. Thank you, everyone, for this opportunity. My name is Benjamin Oberholzer, as Ashley has introduced me. I'm going to be presenting on the raising of Gcuwa Dam, in particular the detailed design phase, which we have undertaken here at the Department of Water and Sanitation. And we're just going to share some design assumptions, methodologies that we have used, and also lessons learned throughout the process. So a quick table of contents. I'm going to discuss the background and the introduction of the project, tell you what it's all about. We'll discuss the spillway shape and some details, all kinds of things that we fitted into the spillway. Thereafter, we will discuss some stability and hydraulic calculations of the spillway. Following that, we'll discuss some recommendations following the model studies that we performed. We did a 2D and a 3D model study. And finally, Londeka will be discussing the design of the embankment. So some background on the project. Over to the right-hand side, you can see the map of South Africa with an approximate location of Gcuwa Dam. It's in the Eastern Cape, close to the town of Butterworth. If you drive on the N2 from East London to Mthatha, on the N2, you will pass through the town of Butterworth, and Gcuwa Dam is situated just about 1 kilometer north of the town. It acts as a balancing dam for the town of Butterworth. Upstream, there's a larger storage dam called Gcuwa Dam, and then water is released down the Gcuwa River all the way until the Gcuwa Dam, where it is retained and then released to the water treatment works at Butterworth. So it's used mainly for domestic water at the town of Butterworth. So just to show you around the dam a little bit, the dam is a 19-meter high composite dam. Composite meaning that it's constructed of both concrete and earthfill. You'll see a concrete portion here on the right-hand side and an embankment portion here on the left-hand side. Just note, I'm going to be using left and right as we are used to using them in the field of dam design. And that's from the viewpoint as if you are standing on the intake tower and you're looking downstream. And the right would be like where the Swandabel is situated, and the left would be towards the embankment. So that's the terminology that I'm going to be used for the duration of this presentation. So Gcuwa is a category 3 dam. It's a medium height classification, but a high hazard classification because the river downstream passes directly through the town of Butterworth. So it's categorized as a category 3 dam. It was constructed in 1972 and subsequently rehabilitated in 2008 to provide it with some additional flood handling capacity. And the storage initially was 1.75 million cubic meters, which is pretty small in the larger scope of things compared to some of the larger dams that we have in South Africa. But it's a very important dam for the town of Butterworth. It's their main source of water, and it's something they value very much. So to show you around, water comes in at the top here. The inflow makes nearly a 90-degree turn over the spillway and then down the Gcuwa River and exits at the bottom of the screen. On the right-hand side here, we have the spillway that is more or less divided into two halves by the intake tower here in the middle. We've got a defunct radial gate, which used to house a radial sluice gate, but that turned out not to be very effective in scouring the dam, so it was filled in with concrete during the 2008 rehabilitation. On the left, as I said, we have a homogeneous earthfill embankment dam with a mechanically stabilized earthfill wall. It's this gray area on top. Mechanically stabilized earthfill is basically a vertical wall of earthfill with panels on the sides. You probably have seen these next to some road cuttings. And then down here we have a causeway through which the river flows. And in particular, I'd like you to note the shape of the natural ground level downstream of the dam. You can see the rock starts very shallow on the right-hand side and then slopes downwards on the left-hand side. It's much higher, with the depth from apron to the crest. So this is a pretty interesting configuration that will have some interesting discussions during hydraulics and stability. So what is the problem with this dam? Why are we raising it? The problem is sediment migration. This is a video, an image taken from within the dam basin during a very dry period. You can see the spillway here. There's the intake tower that I've just shown you. And you can see that this dam is nearly silted up to the top. There's about 2 or 3 meters of storage left here. While just over the wall, it's a 19-meter drop down to the apron. And that's a big problem. For those of you who don't know what sediment migration is, it's just sand or other particles washing down the river, and they don't have enough capacity to be taken over the spillway, so they settle down in the dam basin and get trapped there. And it reduces the storage capacity of the dam. So you don't have as much capacity to work with. So a feasibility study was done in 2019 to decide the best way of reclaiming storage capacity of this dam. We investigated the raising of the dam, which is what I'm presenting now. We also investigated desilting, taking out of the silt and depositing it somewhere else. We investigated using a pipeline from Gcuwa Dam, or installing a pipeline directly from Gcuwa to the town of Butterworth, and also investigated a borehole field in the dam basin. Now, from all of these 4 options, the raising of the dam proved to be the best immediate solution. So that is what we embarked on with the detailed design. So just to show you some graphs regarding the sediment migration. At the bottom here, we've got the year from 1972, when the dam was built, right up till sometime in the future, 2060. And on the left-hand axis, we've got the available storage capacity. So you can see that this dam started out at 1.75 million cubic meters, and then through the years, it started reducing due to sediment migration. Currently, we are at this point in time, and the latest capacity survey taken showed the capacity to be about 0.422 million cubic meters. So if we raise the dam now, it'll bring the capacity back to 1.12 million cubic meters. And that'll give us about a 30-year time period before sediment will fill up that additional storage capacity again, and at which point the problem will need to be addressed again. So some of the proposed upgrades. This is an image showing the dam from the downstream side as you were standing, as you would see if you were standing downstream and looking upstream. So some of the things that we would like to do during this raising, first of all, is to raise the spillway by 1.5 meters. This line showing that. We will also be extending the spillway towards the right-hand side by about 20 meters, adding blocks 15 and 17. We will also be demolishing the bridge on the right-hand side to allow for some increased spillage capacity. On the left-hand side, we'll be raising the bridge to cater for the raised flood levels. We will also be raising the intake tower in order to cater for the raised spillway bridge, because you need a way of accessing your intake tower at any point. On the embankment side, this is a drawing showing the embankment here on the left-hand side and the spillway on the right-hand side. So the embankment will be raised by 1.2 meters and a further 0.4 meters, which is currently under investigation with a model study that we are doing. At which point, we will also be installing a chimney drain and a new tow drain as well, which Londeka will be telling you a little bit more about later on. We will also be strengthening the embankment retaining wall, which is not being discussed in this presentation, but it's also a pretty interesting subject. So let's discuss some spillway shape and details. So as I've shown you before, this is the view from the downstream side, and you can see from this elevation view that here on the right-hand side, it's the depth to the apron is much lower than it is on the left-hand side. So this makes for some interesting calculations when you're doing stability and hydraulics. And it also makes for 2 different profiles. So on the left-hand side, we have a profile that looks like this. My pointer is now showing the existing spillway, how it looks like. And then we are raising it by 1.5 meters. But after doing some stability calculations, we have seen that we need to include about a 3.5 meter step in a downstream direction, just to cater for stability and to give this section enough volume and enough concrete to be stable against sliding and overturning. Over here, you can see a 3D little model of what the spillway looks like. There's the OG spillway. We've got the step here and the downstream face. And here we've included some trapezoidal splitters, which I'll be discussing a little bit more later while we're discussing the model studies. Over on the right-hand side, we have a much smaller section, as you can see by the relative size of these two. It's a much smaller section. Here is the existing spillway, what it looks like. And then we're raising the spillway by 1.5 meters, but you'll see that it's a much flatter OG curve than on the right-hand side, sorry, on the left-hand side. And this is also due to stability calculations. For this section to be stable, we had to make it a little bit wider, a little bit fatter, so that it can be able to withstand forces from water in the dam basin. And I'll also discuss that a little bit later on. So discussing some spillway details. This is a section taken through the left-hand side spillway, which is the higher one of the two. This green part represents the existing spillway as it is now. And this blue part represents the concrete that we would like to add to this spillway. So the problem with adding new concrete is once that concrete starts to set, it wants to contract. And that induces some tensile pressures in the concrete itself. And that can then be transferred onto your existing spillway, which is a case that has not been designed for, most likely. And if tensile stresses are transferred onto your existing spillway, that could lead to a crack formation, maybe down here below or anywhere on this upstream face, which is not a good idea. So to combat that, we are using a fixed and a sliding joint combination. I'll explain them both now. The fixed joint is at the top here and also here at the bottom. And it says here that the fixed joint is doweled into the existing spillway in a way that encourages bonding. We are also preparing the surface to encourage bonding in that area. So this part at the top here and this bottom part is fixed and doweled into the spillway. But then when this concrete starts to contract and then it needs a little room to breathe, we have a sliding joint here, and that's the whole purpose of the sliding joint, to allow some breathing mechanism for the concrete, for the stresses not to be transferred onto the existing spillway. So this surface is prepared in such a way to discourage bonding from taking place. And we're also fitting it with a drainage here at the bottom, section for drainage, which I'll be discussing next. So looking at this image in your bottom right, this is a drainage section that we are including here. And over on the left-hand side image, this is a close-up of the drainage system that we are using. So I'm going to just be explaining what we have here. We have quite an elaborate drainage system. So number one is some concrete half rounds. As you can see by this yellow line going down here, and also the one going out horizontally. And these are also shown here. And there's one going transverse, and then there's two of them going out. So these concrete half rounds are placed over the spillway joints and also in the middle of the spillway joints. And the idea is that any water that comes through the spillway joint should be caught up by these concrete half rounds and then diverted along this network down out to the spillway toe. We also have no fines concrete strips, as you can see by these dark patches underneath the concrete half rounds. And these also just act as another barrier any water running down the spillway here that might be getting behind the sliding joint will be caught here and then transferred out towards the toe of the spillway. Number 3, we have some telltale pipes. Number 3 is shown here by this reddish line here. So this is just a way of alerting us if anything should go wrong. If this drainage system gets blocked or it becomes not functional in any way, water will push back up out of the telltale pipe and we'll see some water leaking out here. And as soon as that happens, we'll know that the system is blocked and we'll need something to alleviate pressure. We need to do something to alleviate pressure. Number 4, we also have some pressure relief holes, which you can see drilled from the bottom of the sliding joint downwards and also inclined underneath the existing spillway. You can see them also on the left-hand side here by these 2 blue lines. So these act as to alleviate foundation, uplift pressure in the foundation. This dam does not have a gallery to do that, so we're also using the drainage system for that purpose. So any uplift pressure can then escape along this line and out to the spillway toe. So let's discuss a bit about stability. We use the classical method to assess the stability of the spillway. This is just a free body diagram showing some uplift pressures and water pressures from water in the dam basin. We've got some silt loads, tailwater loads, as well as earthquake loading. Now, I'm not going to bore you with all the safety factors and tables, but this is the method that we use to ensure that the dam is safe against overturning, against sliding along its base, and also against excessive forces. And we also obviously did this for both the left-hand side spillway section and the right-hand side spillway section. Interesting thing to note is the sliding joint section in the middle. It needs its own stability analysis, because any water that might be entering through a weak point in this contact would come down and come and sit here right at the back of the spillway of the sliding joint, and then this point here would experience the exact same pressure as this point here in the dam. So we all know that water pressure depends on the horizontal height of the water above the point at which I'm measuring. And so this sliding joint will be subjected to nearly the full force of the water in the dam basin should any water leak into here. So for this reason, we did a stability calculation of the sliding joint by itself and shown that it is safe, and then it won't be overturning, it won't be sliding along its base, and also won't be experiencing excessive forces. Discussing some hydraulics now. Spillway capacity is usually calculated by this formula here, which shows that the flow is equal to a coefficient, which depends on your spillway type, and times the length of the spillway, times the height of water on top of the spillway, raised to the power 1.5. But there are certain factors that influence the spillway capacity, such as the OG shape. We have a different OG shape on the left-hand side than on the right-hand side, so that is different. The depth of approach, if you paid attention on that sediment image that I showed, you would have seen that the depth of approach is different on this side than it is on this side. The depth of the apron obviously is much different. Here it's much higher than on the right-hand side. And also the tailwater level has an influence. So it's difficult to assign one value for each of these criteria in your spillway calculation, discharge calculation. So what we did was to split up the OG into 4 distinct regions, each with its own criteria. And then we solved those 4 equations simultaneously. So we had 4 different OG profiles, each with its own parameters according to this criteria, but all having the same H or height above the spillway crest. And we then solve those 4 equations simultaneously to arrive at a spillway capacity. So the end result was this discharge rating curve, which we all know. At the bottom here, we've got the flood magnitude. And on the left-hand side, we have the flood water level in the dam basin. And you can see this blue line represents the combined spillway discharge capacity of Gcuwa Dam. That is now for both the left-hand side spillway and the right-hand side spillway. So talking a bit about flood routing. We did flood routing at the dam. For those of you who don't know what it is, it's just routing an incoming flood through the dam and seeing how the water level in the dam reacts to that. So your dam has a finite volume, and then we divide the incoming flood into various time steps, and for every time step we calculate a change in volume. So change in volume, this is a pretty interesting looking equation, but it's not that difficult. Change in volume is just the change in the inflow, which you get from the inflow hydrograph, minus the change in the outflow, which we get from this graph that I've shown you just now previously. And from that, once you run that for a couple of time steps, you can get a good idea of the outflow of the flood from your dam, and also the water level inside the dam. So this is the result. You will get an inflow hydrograph and also an outflow hydrograph. So you can see from this, the blue one is peaking out right below the red one, showing that these two are plotting virtually on top of one another. And this shows that Gcuwa Dam does not have attenuation capacity. It cannot dampen an incoming flood as larger dams are able to. So we regard the incoming flood as this being the same. Sorry, we regard the outgoing flood being the same as the incoming flood. There are also guidelines by SANCOLD that says if the attenuation capacity is this low, then you should take the entire incoming flood as the outgoing flood and design for that. Discussing some freeboard, we did calculations both according to the SANCOLD 1990 guidelines and also the SANCOLD 2011 guidelines. And in both of these, you have various events that happen, and these are combined according to combinations. And then these are added up towards the side to give you a height of freeboard that you require. For those of you who don't know, freeboard is just the height above your full supply level to which the water can rise. So then it's a way for you to determine how high the non-overspill crest should be. So in both these cases, the SEF flood was the most critical one, largely due to the dam not having any attenuation capacity. So we went for a freeboard of about 5.7 meters, which we are still busy also revising, as I said earlier, by doing a 3D model study. So I'm going to be talking about the model study next. This is an image showing the model that we set up. Firstly, we did a 2D model study. This is the first one that I'm going to show. So water is flowing from your left-hand side to your right-hand side in the direction of this arrow. This is basically a channel that was built with a plywood on the far side and a perspex window on the front side, which you can see. And it's there so that you can look through the perspex window and see what the water is doing. So we've got the 2D spillway fitted here, basically just a slice of the spillway that was cut out. There's a stilling basin here at the bottom, which we are using to estimate scour potential of various spillway configurations. And then there's a tailwater gate located at this point. So if you were to stand here and look up into this channel, you would see this view on the image on your right, with the tailwater gate being situated here. And this tailwater gate just allows us to adjust the tailwater by adjusting this screw up and down. And it allows us to control the tailwater on the spillway. So water flows down the chute, over the spillway, across the stilling basin, across the tailwater gate, and then through the wave suppressor. We've got a wave suppressor here and another one that is down here, which you cannot see. And then this just calms the water to pass over a crump weir at the bottom of the channel, which we use then to measure the flood going over the spillway. So water levels are measured using point gauges. There's one up top here sticking out there behind the brick wall, and that one measures the water level on the in your dam basin or the head on the Oji crest. And then there's 2 point gauges here for measuring the tailwater gates. Oh, sorry, the tailwater levels. So the main point of this was to check the actual capacity of the spillway against theoretical calculations. And this is a pretty complicated looking graph. It was set up by my colleague, Chris Hatton, and he gets all the credit for this. It's a pretty robust graph, so let me explain what happens. This blue dotted line here shows the theoretical discharge curve of the left-hand side spillway, which is the higher one of the two. As you can see, there are a couple of configurations that we've tested here. And these dots show the actual results for these various configurations. So you can see right from the start that it follows pretty much the theoretical calculations as we have expected. And then when the flood becomes a little bit higher, then it starts to break away, shown by this little pink line going here. And the water level, the waterhead becomes a little bit more than what we have anticipated for a given flow. On the left-hand side, you can see the same curve for the smaller OG, the right-hand side OG. This green line shows the theoretical calculation, and then the dots just show the actual values for this spillway section. So I'm going to discuss now the protrusions that we also tested. This was a secondary aim of the model study. We tested various protrusions, as you can see, 1, 2, and 3. First one was just a conventional Robert splitter. For those of you who don't know, these protrusions are used for energy dissipation. So water coming over the spillway passes through these structures and gets aerated, and the energy gets dissipated so that the water falling onto the downstream side of the spillway is not too destructive and does not erode away your apron. So number 2, we have a trapezoidal protrusion, which we tested. This is basically just a Robert splitter that is filled in with concrete at the bottom. Number 3, we had 2 rows of splitters. And number 4, we also had 2 rows of splitters, but this test did not give very good results, so we decided not to include it going forward. So these 3 structures were then compared using a scoring matrix, which we gave each one a point out of 5, with 5 being very good and 1 being subpar, for various criteria. First one being hydraulics. So number 1 and 2 performed pretty well in terms of hydraulics. They performed very similar to one another, while number 3 performed a little bit less satisfactory because it did not reduce the spread of the water by as much as the first 2 options. Secondly, material volume. Option 1 got the highest rating with 5 because it requires very little material, although it does require steel because of this cantilever behavior. While number 2 and 3 both received 4 because they require a little bit more material and they would therefore be a little bit more costly. Constructability-wise, option 1 was assigned a 4 because it requires scaffolding to be erected below these structures in order to build them, while option 2 and 3 would be much easier to build because they are on top of the existing spillway, or on top of the raised spillway. You don't need any scaffolding to support them. In terms of durability, option 1 was given a 2 because of its tendency to break off or to shear off by falling logs 3. Option 3 was given a rating of 3 just because it has long edges, and those edges are prone to being weathered by falling water. Moving on to the 3D model study, the image on your right is a top view of the model study. Water enters the model through this inlet pipe here and then flows in this direction. We've modeled the sediment in front of the spillway using cement and or concrete that is filled in between these sections. And here's the spillway section and the embankment section. So we're now looking at the dam from within the dam basin. There's a causeway down here at the bottom, and then the river leading down. And then at the bottom here, we also have a crump weir structure, where we can measure the flow of water coming over the spillway. To the image on your left, this also shows the right bank spillway on the side, the left bank spillway. We've got the embankment here, flow going in this direction, and there's a stilling basin here, which is used to calm the water going downstream. So model studies always make for great videos. So this is a video that I'm going to play. As you can see, water is running over the spillway. Water on the right-hand side is running over the spillway, doing a hydraulic jump, and then makes a nearly 90-degree turn and is thrown towards the left-hand side, while water running over this portion of the spillway passes through the splitters, the aerators, and then encounters the stream coming from the right-hand side. So this just shows why a 3D model is so important to do, because this water coming over the spillway encounters this sideways moving stream, which is nearly impossible to predict using conventional spreadsheet calculations. And it's important for us to do a model study just to incorporate all these activities that the water might have. This is another video that I'm going to play. Shows water coming over the right-hand side of the spillway, passing towards the left-hand side. And you can see here at the bottom that water is totally outflanking the retaining wall that we made for it. It's also outflanking the embankment retaining wall on this side. And down here, you can see the causeway, which is shown to be a little bit, it doesn't have enough capacity to transfer the flood. Keep in mind that this is a really large flood. I believe this was 1 in 1,000 flood. So in cases of this, dams are allowed to withstand some damages, but they should not fail according to SANCOLD guidelines. So one of the main outcomes of this study, again, was to test the actual data, actual spillway capacity against theoretical curves. So this is now for the combined spillway, both left and right. Again, this chart was set up by my colleague Chris Harting, and he deserves great credit for this. So as you can see from the start, these data points, these circles, show the actual values, and they are a bit higher than the theoretical values, meaning that at any point along this curve, at any flow rate, the water level above the crest is a little bit higher than what we have anticipated it to be. And this is also the reason why I shared with you earlier that we need to increase the NOC by a further 0.4 meters due to this fact. This might be due to various reasons, like the right-hand side spillway drowning out, and the water levels, the tailwater levels on the left-hand side of the spillway being a little bit higher than what we anticipated because of the crossflow from the right-hand side, causing the spillway to drown out in general, which requires us to provide a more freeboard. So it follows generally the same curve as a theoretical calculation, but at some point it starts to break away at higher flows, as you can see here, and it's becoming even less conservative. and the water levels are becoming higher than what the theoretical values are. So here's some beautiful photographs that were taken during the model study, and together with that, some recommendations that were made. One of the main recommendations was that the NOC should be raised by an additional 0.4 meters, which we are currently in the process of getting to and incorporating in our calculations. The left bank retaining wall also needs to be fitted with a wave deflector. This is now this retaining wall onto which we saw the water running. So it should be maybe just raised in general to be able to handle the flood water that is coming its way. And also we need to increase the carrying capacity of the causeway downstream. So with that, I'm going to give over to my colleague, Londeka, and she'll be telling you more about the embankment.
Okay, good afternoon, everyone. Okay, the embankment design, which is the part that I was designing, there were key aspects that I had to look into, which were to provide for the required freeboard and also to stabilize and improve the safety of the embankment. With that being said, 1.2 high parapet wall was proposed to safeguard against overtopping, as Gcuwa Dam is an earth embankment dam. In addition of a filter drain, if in a fill material on the downstream slope of the existing embankment was proposed to stabilize and improve the safety of the dam, and also the riprap on the upstream slope of the dam. Okay, zooming into the configuration of the embankment, as I have said, the 1.2 parapet wall, as can be seen, and also the filter drainage, which is a chimney and blanket drain, that will be 1 meter thick. This will be augmented by a filter geotextile. Also, the additional fill material having a slope of 1:2 vertical, 3:2 horizontal, which is protected by the 300 millimeter thick crusher run. This is the 75 millimeter stone size that we'll be using. And the upstream riprap on the upstream slope of the dam. Going further into the additional fill material, the key aspects that were taken into consideration in the design of this fill material is that we had to consider whether it should be earth fill or rock fill. And with the rock fill, we had to look at the founding levels for the rock fill that is required. And this was a hard rock or moderately to slightly weighted bedrock. And this level required deep founding depths. Deep founding depths that were ranging from 10 meters to 16 meters. And from the geotechnical investigation that was done, it was found that there is a water table that exists at a depth of about 7 meters. So the use of this material is going to lead to large excavation depths and having to deal with water during construction. Now looking at the earth fill material, it had to be founded on residual metasandstone on the lower left flank of the embankment, which is ranging to a depth of up to 3.5 meters. And on the upper left flank of the embankment, it have to found on highly weighted residual dolerite, ranging to a depth of up to 2.5 meters. The use of this edgefill material, was more favorable in that the excavations are more shallower. Initially, the proposal was to use the edgefill material that is of semi-pervious nature as the additional fill because of its benefits in terms of permeability. However, from the geotechnical investigation, it was found that there isn't enough of this material available within the borrow areas that we looked, which were within the dam basin. And a large bulk of the available material was more of an impervious material. Now, zooming into the stability of the embankment, the load cases that were considered were according to the U.S. Army Corps of Engineers, which is the end of construction, the steady state seepage, rapid drawdown, and also the earthquake loading. This was also, we also have had our own approach, which is from our design criteria memorandum, which included rapid drawdown that is with seismic loading, and also end of construction that is with seismic loading. According to the seismic hazard map of South Africa, the site-specific peak ground acceleration for Gcuwa Dam site is that of 0.04, and this value was used as an operating basis earthquake. Now, looking at the material parameters, we had to adopt from the geotechnical investigation the drained material parameters, which were used for the steady state seepage condition. This means that all materials here are considered to be drained and effective strained parameters are used. This was the geotechnical study made a recommendation that the homogeneous existing material, its effective parameters had to be, for design purposes, we had to adopt zero cohesion for the steady state condition. Looking at the undrained parameters, the undrained conditions, which are relating to the end of construction and the rapid drawdown condition. The undrained shear strains here were used for materials that are fine-grained with low permeability, while the effective shear strains were used for materials that are free draining. For the end of construction case, an RU factor of 0.1 was assigned for this case. This means to account for the poor water pressures during construction as the material is placed. Now, looking at a normal homogeneous section, according to the USBR, we looked at the effects of providing internal drainage, where you can see in the diagram at part A that for a homogeneous dam, the likelihood of having a phreatic line daylighting on your slope, unless you have an internal drainage system that is able to lower your phreatic line and bringing it to your selected collection point. Now, looking at the existing embankment without the proposals for the raising, the analysis of a seepage analysis, we were able to get the seepage line almost the same as what I've just mentioned earlier. And it should be noted that the homogeneous embankment was separated into two layers. We were having an upper layer and a lower layer, which according to the rehabilitation of 2008. These layers differed in the shear strain parameters. This was also confirmed as part of our geotech study that was done in 2020. Now looking at the modified embankment, where we now introduced an internal drainage system. This is a chimney and blanket drain. There was a change in the phreatic line being lowered, allowing us to collect seepage at the toe of the embankment, which was selected as our collection point. So the internal drainage system was providing for conveyance of seepage to collect at the selected and manage at the selected drainage point, which was at the toe of the dam. Now, going into the slope stability analysis, the load cases, as mentioned earlier, were now analyzed using the limit equilibrium methods. These are the methods that uses the method of slices, where more Coulomb criterion is applied to calculate the factor of safety. And the results demonstrated that the design raising satisfied all the minimum required factors of safety. In addition to the deterministic slope stability that was done, a probability and sensitivity analysis was also performed. Here we were using the slide software for all of the deterministic probability and sensitivity analysis. And the probability and sensitivity analysis was done to consider the variation in the shear parameters as seen in the images, where we see the existing lower layer of the embankment, the angle of internal friction, the variation in the friction, and the variation in the cohesion. And these were from the drained shear parameters. This analysis, the probability of failure was calculated, and this is the probability that the factor of safety is less than 1 for the range of the material parameters that is considered. This was used as a level of confidence that can be placed in the design. And the findings were that the probability of failure for the rapid drawdown with the seismic loading resulted into 11.4%, while the probability of failure for the end of construction with the seismic loading resulted to 6.1%. And for all the other cases that were considered, a probability of failure of 0 was obtained. As I mentioned, this was used as a level of confidence that can be placed in the design. Now, zooming into the toe drain design, we looked at the seepage analysis, where we need to estimate the amount of seepage that will need to be managed. And here, 4 cross sections along the length of the embankment, which were spaced at 60 meters apart, were taken into consideration. And using the slide rock science software, the seepage at each cross section estimated, resulting into a total volume of seepage of 0.2 liters per minute. Knowing this information allowed us to be able to provide the required drain pipe size that would be able to drain the seepage and allow us to maintain it at the toe drain. Now looking at the drainage of the storm water of the embankment. Zooming into the crest, we have a parapet wall on the upstream, and the idea of having a parapet wall was to act as a barrier for the different floods that we might experience for this dam up to the SEF flood. And the drainage for this dam now the crest was designed to drain to the downstream side of the embankment. Reason being that we couldn't drain to the upstream as normally done, as it's an embankment dam, it's an edgefill dam where we don't want overtopping to happen to this dam. We have to safeguard it against overtopping. So this parapet wall had to be designed to be watertight. Lessons that I learned from this analysis, the overall embankment design was from mostly the slope stability, where we performed the probability analysis, and we found probabilities that are exceeding 1%. And for these cases that were considered, these probability were accepted, taking into consideration that the rapid drawdown with seismic loading is quite a severe load case, which is mostly applicable to dams that are used as pump storage. With that being said, this covers the embankment design part for Gcuwa, for the raising of Gcuwa Dam. Thank you.
Thank you. I would like to thank Benjamin and Ndeko for their very informative and detailed presentations. Your effort and time is appreciated, and I think everyone is encouraged by the work you have done. So there are a few questions in the chat. If anyone in the audience wants to ask any more questions, please go ahead and type them in the chat. I'll give some time. There's at least some time still left. And then if you really don't want to type and have a long question, you can raise your hand and then I will activate your mic at the end of reading the chat questions. All right. So the first question we have is regarding the drainage. So I'm guessing this is for Benjamin because it was a little bit earlier in the chat, but maybe if there's something applicable to both, please feel free to answer. Was there any consideration given to directing the new drainage back to the existing drainage gallery?
Okay, so am I audible?
Yes.
Okay, so there was no existing drainage gallery. From what we can see on the asphalt drawings, it's a solid dam. There was no drainage that we know of. There's no gallery. So we had to make everything, all the drainage that is there had to be made from scratch. So yeah, it was not rooted into the existing drainage.
All right, thank you. The next question is, at what scale was a 3D model tested?
3D model was tested at a scale of 1 in 70. The 2D model was tested at a scale of 1 in 25, which is a bit larger. And the main limitation for these was basically just the pump capacity at the DWS hydraulic slabs. My apologies, I should have mentioned earlier that these model studies were done at the DWS hydraulic slabs in Pretoria West. So the main constraints for the model size was the pump capacity and also the capacity on the floor, the space on the floor that we have to build the model. But the pumps was primarily the deciding factor. So for the reason the 2D one could be done at a larger scale is because we were only testing one spillway section at a time, so only the left-hand side or only the right-hand side. So you could only use that representative portion of the full flood. So you could then up the model because we have more pump capacity.
Thank you. So a related question, the next one is, how did you validate your model and overcome some of the limitations of scale models as opposed to computational numerical models, i.e. friction effects, turbulence, and other physical effects that can be inaccurate for physical smaller scale models?
This is quite a difficult thing to do. I would say a physical model study is one of the more, how can I say, it's a better way of estimating the flow in your dam compared to software models. And it's a difficult thing to calibrate your model in these cases. We try just to have the roughness similar to what it would be in the field. We try to construct the model as close as possible to what it would be. One thing that we could calibrate actually was the tailwater levels. The tailwater levels proved to be pretty high for Gcuwa Dam, much higher than for normal dams, or not normal dams, for other dams. And we could check that during a recent flood that was there, so we were able to estimate the flood at that point.
Thank you. The next question is, the raising of the dam was based on sediment generation for the next 30 years. Will this dam be raised again after 30 years? And was there any appropriate drawdown flushing scheme of sediment considered?
So yes, it has been shown that this sediment migration will become a problem again in about 30 years' time. So we are hopeful that another solution will be in place at that time. It's a definite problem. Currently, Butterworth is experiencing water restrictions, and it's a very pressing issue at the moment. Some community action from time to time, and it's something that must be addressed very urgently, which is why we are doing this as a short-term solution. The dam will not be able to be raised again, at least from what I've looked into, because of just constraints of the geometry around the layout of the land. If you were to raise the dam, you would start outflanking some of the slopes, so it won't be able to be raised again. So at that point, we will need another solution, and our planning division is definitely working on a solution for that.
Okay, thank you. The last question in the chat is, at a scale of 1 in 70, what do you estimate was the accuracy of the measured flow?
I don't really know. I don't know how to answer the question. We did not check the accuracy of the flow. What we did check was the model, how much water that the model lost during the testing. That was a very small amount. It was about 0.9 to 2% that the water that the model lost. So yeah, I'll have to do some calculations before I can answer that question completely. I'm sorry.
All right, thank you. If anyone has another question and they want to raise their hand, please do so now. All right, Alan Shamali, I will allow your mic now. Please unmute yourself and then ask your question.
Thank you, Ashley, and thanks, Benjamin, and your lady colleague. That was an excellent presentation. What I have to ask or convey or share is too long to type. Benjamin, would you be able to put the slide on the screen where it showed your cross-section with the drains? It might be easier for everyone to see. And then I'll continue. It's where your drain holes into the rock mass of the foundation intersect your semicircular drains going out horizontally.
Is this the correct image?
It's loading at the moment, Ashley. There's a lag in the signal. It's still loading. Okay, I will describe it. Benjamin, you have your drain holes into the foundation are most probably 75 or 100 millimeter diameter holes going into whatever depth as you as designer have deemed necessary into the foundation and the rock mass. I understand that then meets semicircular pipes to flow out, for any seepage to flow out horizontally, bearing in mind that the life of the dam after this will be 30 years, or it could be 30 plus. Over that period, and as you have in most dams that do have galleries, there is provision to now not only re-drill those, but ream those holes. I would have thought in that case it would be best to extend that pipe where it meets the circular horizontal hole, extend it to that step that's above there, and have a provision where you have a collar and a cap that you can unscrew, all level with the step, the horizontal of the step, so there'd be no cavitation problem. And then in X years to come, or you want to check several of them, you could just unscrew the cap, ream it, or flush out the holes. I'm just passing this on because this has been omitted from a number of dams that don't have galleries. So you and your colleagues might like to comment.
Yeah. Hi, Alan. Thank you for the very great comment. I think it's a fantastic idea. It was not considered at the moment, but I think it's a worthwhile thing to consider, and it won't be a difficult alteration to make. Yeah, a gallery was too small to fit. Well, let's say the section was too small to fit a gallery in there, so precluding us from opening the holes if they are closed. So this would be a great option to do that. And the geometry also suits it pretty well. With that being said, we have analyzed this dam to its fullest extent, assuming full uplift pressure, that these drains are clogged, drainage system is clogged. And so even though we are providing the drainage as a belts and braces approach, the dam would still be stable under full uplift conditions. But thank you for the suggestion. I'll definitely incorporate it.
Thank you. And if I could just add on, at what intervals are those drain holes into the paper or in plan?
So right now, this is a best spillway block. You can just see get my pointer going here. Pointer. So this is the width of one spillway block, one typical spillway block. They differ a little bit from block to block, but it's about 9.3 meters. So these are about, let's say, 2 meters here and 2 meters there, with about 4 meters in the middle, 5 meters in the middle, if my calculations are correct. But these will definitely be also moved on site due to the varying conditions we have there in the downstream side. The mass, sorry, the rock mass, it's sloping upwards towards the right-hand side, looking downstream. So at some point it might become difficult to put these exactly where they ought to be on the drawings. So I think this will also be a great exercise on site to ensure that we can provide ample drainage for those drainage holes.
Thank you very much. Thanks, Ashley.
Thanks, Alan. Is there anyone else that would like to ask a question? You're welcome to raise your hand.
I believe there was one in the chat by Eunice Muddy.
All right, let me read that one. During the feasibility study, by what factor or order of magnitude was the raising option preferable to desilting of the dam basin?
So our calculations was, or the feasibility outcome was largely a financial one. And we did, in the feasibility study, we checked the cost estimate for both of these, well, all four of these options. And the desilting of the dam turned out to be much more expensive. I think it was more than double what it would cost to raise the dam. At first, this quite baffled me. I could not stomach this pretty well, but in other literature, we also found the same trend, that desilting the dam cost much more than raising the dam. Well, let's say you can get the funds. It's also a matter of where do you put it. It's quite an environmentally touching subject. Well, what do you do with this sediment? Some people say you could use it for fertilizer or for brick making, but you will need a market to be able to get the silt out and use it somewhere. You can't just go dump it anyway. So in terms of order of factor, I'd say maybe a 2 or a 3, that the raising was more preferable purely based on cost.
Thank you. There's a raised hand, so Lucy Niflis, I will allow your mic, and then please just unmute yourself. And all right, your hands are down.
Yeah, sorry, that was an accidental hand, but while I'm on, I'll just say thank you to Benjamin and Lodeka. Really enjoyed it and learned quite a bit.
All right, thank you. Tilman, your hand was up for a brief second. Was that a mistake as well? All right. So any more questions? Any more raised hands? It was very interactive. I thank you so much. Alan, please go ahead.
This is for Londeka. Did you say that on the downstream face of the dam embankment, now I know it's DWS practice on really big dams, did you say on the downstream face of the dam you've got a layer of crusher run? Is that correct?
Yes, that's correct. Crusher run will be provided as a slope protection on the downstream face of the embankment.
Okay, and then whilst you're there, if you can recall from your design, is that how thick is that crusher run? Because I'd just like to give you some feedback from other dams.
Okay, the crusher run is 300 millimeters thick.
Okay, thank you. I'll now continue. We've had a number of dams in South Africa, a number of ones that don't belong to the department, but let's take Gauteng. We've had a number of dams that didn't have that. They had just normal earthfill. In fact, they had an overgrowth of vegetation. And we found with not only storm rainfall, but with cloudburst rainfall, we found that material of the type of crusher run and smaller, not as strong and not as thick, has actually been badly eroded. Not it all having been eroded away, but you've had gullies on the downstream face. So I'm just passing that on, because when we assisted DWS for the embankments on via TCTA for the big line dams for Olifants Phase 2, some of the embankments were 15 meters high, and at that time, those in engineering services, they required they required a thick layer of rock. Now, I know that's more expensive, and then again, there had to be a bit of a transition to the rock. But again, I'm just passing this on in the context of a crusher run and its thickness, fully realizing that you have quite a flat slope on the downstream side. Thank you.
All right, thank you. Nodeka, did you have any other comments?
No, Ashley. Thank you, Ellen. I think we'll look into the thickness and going forward. But I think the provided one should be fine for this, because the size of the crusher run, these are 75 millimeter stone sizes.
Thank you for the feedback.
Thank you.
Okay. I don't see any more questions in the chat. We still have quite a few people that's still hanging around. So if you have any pressing questions, please, I'll give another minute or so for a raised hand or a question in the chat. All right. This is the last event for the SANCOLD YPF calendar. The next pressing matter is obviously the SANCOLD conference. If anyone is going, please note that the Wednesday evening we have the SANCOLD Young Persons Forum meeting and social event, but it's also free for other delegates that will be attending the conference. There will probably be something fun happening, so if you are going, please don't miss out on that evening event. I see one more question from Wally in the chat. Seeing that this is a Category 3 dam, is the APP appointed as well as the professional team?
Good day, Wally. Yes, well, the APP did serve his term before he resigned, and the professional team at that point was also appointed for the design. And when we submitted for design for the license to construct, these were all in place. But subsequently, the APP has now resigned, and we are waiting for another APP to come on board. So we are in a transition period at the moment.
Yes, Alan, please.
Last one. Thanks, Wally. While we are there and while we've got quite an audience, and I might not have an opportunity at SANCOLD, you know how busy we are. I noticed we got there with the Londeka and Benjamin, looking at the experience. It's a case of, I know the department, I know Wally, I know many of you, Comfort's on the EXA committee for APPs. We would be looking forward to you, Londeka and Benjamin, to receive your applications to be the APP for a task at some time, because as you know, a burning question is that we're short of young APPs and APPs, and the sooner you can get your foot in the door, the better, because this crops up time and again. Please, please. Thank you, Ashley.
Thank you. All right. Yes, it's quite obvious that DWS projects are interesting for the SANCOLD members. So if you're from DWS and you'd like to take part in one of these webinars, please contact me. I'll help you in getting the correct approval and with the project ideas. We really encourage you. We'll probably be doing a couple of webinars again next year. So please feel encouraged, please feel inspired, and come and share one of your projects with us. SANCOLD is genuinely quite interested in that. And also thank you to DWS for colleagues for coming and showing your support. I really appreciate it. So I probably won't see you at the conference, but thank you so much for coming today and for having such a interactive session. Really appreciate it. Really appreciate the turnout. Hope you have a good evening further. And thank you so much to Benjamin and Ondeka for your wonderful presentations and all the time you put into coming and sharing with us. Really appreciate it. I cannot say enough how much I appreciate it. So thank you. And well done. Well done. Right, thank you.
Thank you, Ashley.
It's a pleasure.
Bye-bye.
Bye-bye.
Thanks. Bye-bye.
Thank you, everyone.
Thank you.